This is Lab 3 for Physics 2212 on magnetic fields of a bar magnet. For this lab, we used our cell phones to measure the magnetic field due to a bar magnet, and we specifically wanted to see how the field was dependent on distance. We did this by measuring both the on and off axis magnetic field. This lab included a lot of important physics concepts like the magnetic field, distance dependence, current and charge, and was also crucial to understand the idea of magnetic north and Earth's magnetic field. In order to measure the distance between the bar magnet and the magnetometer chip in our phones, it was first crucial to account for magnetic north. This meant aligning our phones in a position where the x component of the magnetic field was approximately 0, while the net magnetic field was 48 microteslas for those of us in Atlanta. This was crucial because if the x component had not been isolated, results would not have accounted for Earth's magnetic field in the x direction, and our values would have not accurately represented the magnetic field from just the magnet. With all that taken into account, we could then measure the distances for both the on and off axis magnetic fields. Figure 1 shows how the on axis measurements were taken, while figure 2 shows how the off axis measurements were taken. This is the data that I collected and the graph that was generated from that data. As seen by the graph, the natural log of the x component of the magnetic field and the natural log of the distance were negatively related. After seeing this data, I could say that I observed that when the magnetometer is far from the magnet, it measures a non-zero magnetic field in the x direction. This x component can either increase or decrease depending on how the magnet was oriented during measurements. For the question of how measurements would change with two magnets end to end, I believe that they would increase, but only up to a factor of 2 because the two magnets stuck together will be slightly less than twice as strong as one magnet since we use the superposition principle to add those two magnetic fields. With all that data, I could then calculate the magnitude of the magnetic moment mu. I did this using the equation from my earlier graph. This equation gives two important values. The slope gave us the n value, and the y-intercept gave us the natural log of k. By subbing in the known formula for k, I could then manipulate the equations and solve for a mu of 0.3588. Then for my off-axis calculations, I observed that the angle for B net was, for the 45-degree angle for B net was approximately 4.5 times 10 to the negative 5 teslas, and this value was an average of 3 trials. When derived computationally, I got a value of 3.63 times 10 to the negative 10 teslas. This is because my n value is greater than 3, which is the actual value of n, and these differences are most likely due to the presence of items that interacted with the magnetic field, like metal tables or chairs. The first step in modeling this computationally was the magnetic field function. And for this, I modeled the Biot-Savart law for the magnetic field as seen in line 30. And I then created all the different arrows that showed the magnetic fields for both on and off axis situations. All of this code created the following model where blue arrows are off axis, orange arrows are on axis, and the purple arrow is the magnetic field at 45 degrees.